everyone to session 2 of the day. Here, the esteemed panelists are going to discuss about opportunities for exploration and production of unconventional hydrocarbons in Indian basins. For this, we have Mr. Pinakadhar Mohapatra as the chair, and for the co-chair, we have Ms. Sushma Rawat. Ms. Sushma Rawat is Executive Director, Basin Manager of Assam and Assam Arakan Basin, looking after the ONGC's ENP activities for the entire Northeast region. Additionally, she is also the Director Opal of the ONGC Petro Edition Limited. Ms. Rawat was a core team member of Government of India initiative Hydrocarbon Resource Assessment Study for 26 sedimentary basins of India during 2015 to 2017. Under her leadership, basin scale 3D petroleum systems modeling of 11 basins was carried out in ONGC. Ma'am, may I kindly request you to commence the session, please?
Namaskar. Thank you so much, all the presenters today, and the session on exploration and production of unconventional hydrocarbons for Indian sedimentary basins. It is going to be chaired by Mr. Pinakadhar Mohapatra, who is the Director Exploration and Subsurface with the Antelopus Energy currently. He has had 30 years of wonderful and very active experience in the field of hydrocarbon exploration as well as development, and has immensely contributed to a diverse geological setting of all the sedimentary basins of India and a number of acreages outside of India. So with that, I would be inviting all of us to initiate this session. So over to you.
I think we have to go to the first speaker, John. Sushma, you may introduce John Dolson,
yes,
and
okay.
then.
So, yes, I just thought you would like to say something, and then I would commence with inviting.
I think we are already. Yeah, yes. We are already late.
So today's first speaker. So we have the first presentation from Mr. John Dolson, who is the Director, DSP Geoscience and Associates, LLC, and Senior Geological Advisor to Dolson Energy at London. Having more than 35 years of experience in the oil and gas exploration, both in domestic as well as international acreages. Mr. Dolson has also served as the Vice President of the American Association of Petroleum Geologists from 2006 and 2007, and was the Senior Geological Advisor for TNK BP, that is looking after the Russian interests, and Amoco BP before starting DSP Geosciences in 2008. So he would be presenting our first paper today on tight oil, global tight oil and gas, the principles and examples with challenges to India. So it is over to you, Mr. John Dolson now. Thank you.
Okay, well, thank you very much for having me in this thing. I got to say I'm envious. It's 3:40 in the morning here, and you guys are in a nice afternoon there, and maybe you're snacking on something. Anyway, it's I'm envious of your time zone. Also, I'm glad you only gave me 35 years experience, because that makes me younger than I am, because I actually have 43 years of experience in the basins. I'm going to cover principles first here, and then give you some global examples of where unconventionals are kicking off. And it's really important to look at the impact that has occurred, particularly in North America, with the rise of the unconventionals. M. King Hubbard, back in 1956, made a curve that said oil would peak at about 1970, and then it would go dramatically down, and we'd be out of oil by 2020. He looked like a genius for many years, until about 10 years ago, when the Hubbard curve got completely displaced, and we peaked at 13 million barrels a day pre-COVID in the US, and we're at about 12 million barrels a day now. Now, what this is the rise of the hydraulic fracturing and the tight gas shale revolution. I want to say there have been three major developments that allowed this curve to go up. First off was the recognition back in the 70s and 80s that shale and tight gas might work, and that was Fred Meisner, and I'll show you also in the Wattenberg field, it was another geologist. Mitchell came along. This is really a breakthrough. He tested horizontal drilling and fracking for about 20 years before he figured out the Barnett. And what's happened in recent years is we're drilling faster and longer. Some of the laterals in the U.S., this is amazing to me, they're going out 6 kilometers, and these are being drilled under a month to get that rate. So 3 big steps, and historically, it's kind of important to go through that. Now, tight oil and gas, I view it, and I think a lot of other people do, is kind of a modified version of stratigraphic traps. The difference being they're not conventional secondary migration traps. They're traps that occur where the reservoirs are intimately embedded with the source rock in a mature oil and gas window. Everybody's seen that diagram, so I don't really need to spend a lot of time on it. The main thing is we want to have an overpressured basin. We've got to be able to recognize the maturation window, porosity, brittle zone mapping. We can do that with resistivities of shales, test and show status. And the real thing here that makes this work is the rapidity with which rigs are being redesigned, and we're getting deeper and longer laterals out here to make these plays economic. So it's really important to pull all this kind of information together. Now, I love this diagram that EOG puts out. It kind of gives you, when we think of oil pools, of course, the public thinks of a big cave with oil in it, but a really good reservoir, the pore throats are the size of a human hair. Getting down here in 2 Darcy sandstone, this is really good rock. These are really small pore throats by what we think about things. When we get into tight gas, we're talking about pore throats the size of soap film, and shale reservoirs even smaller than that, but the molecules are even smaller. So we're really looking at some very tight rocks, and getting hydrocarbons in there is easy if you're inside the source rock, but a lot harder if you're trying to get those things outside of the kitchen in a migration pathway. Now, I'm going to kind of brush over this stuff at a high level, but when you look at a shale system with gas, there are really 2 types of gases in here. There are gases that are adsorbed onto the organic rich source rocks, and then there's free gas that's down in the pore spaces. And we measure these things with headspace and mud gas and other tools, and plotting that degree of these different types of gases where they're separated can actually give us a kind of a direct look at where the permeability is in shales. If you've worked with shales before, you know how frustrating they are when you look at them quickly. You see what looks like a homogeneous system, but they're not really. They're widely variant, and understanding that variance is really important. Not all shales are equal, in other words. They're all a little different, and they're different within a basin, and they're different vertically when you're working the plays, and that makes a difference. Now, when we start getting into the concept of do we have sweet spots, we really got to pay attention to the stratigraphy, the timing of the burial and emplacement, and whether or not we actually have maturation enhanced traps. Which I'll show you with some examples here where we're overpressured and we're down in that oil and gas window, and that's actually part of the trap. Now, this is an important diagram, particularly for tight oil and gas in kind of what we view as a conventional sandstone or so. And it's one that Keith Shanley put out in 2015. They've had it a number of times. The idea here is that these rocks we don't emplace the hydrocarbons in these really tight rocks. That requires a really long column to do. What we do is, the theory is we emplace these hydrocarbons in these rocks when they are good reservoirs, and that with burial and diagenesis, they basically become worse reservoirs with time. So they end up here, it started down here. And I think that's an important thing to remember. You got to understand your burial and charge history to kind of get a feel for how these rocks are getting the hydrocarbons in them. Now, when we look at maturation and hand straps, sometimes right around the edge of the maturation window, we get some pretty good fields. And sometimes a little bit beyond it, when we're talking about a little bit of lateral migration. And I'll show you some examples. One of the things I always try and stress to people with tight gas and tight oil inside a clastic reservoir, and this could work for carbonates also, is that when you run capillary pressure curves and you get a curve like this, which simulates the reservoir filling with hydrocarbons, but if you release the pressure, uplift the basin, you will get the imbibition curve here, which when it comes down, this gives you kind of a residual saturation. This is something you have to be really worried about because in many of our tight gas basins and tight oil basins, there's been substantial uplift, sometimes kilometers or many miles. And when that happens, these reservoirs will drain their hydrocarbons out and you'll get residuals left. But if the residuals are at 35 or 40, 55%, they're going to look like pay-on logs. And when you go mapping these things out, you won't get any production from them. Best you'll get some water. And this is just something to be a little bit aware of. But as was mentioned in Bob Schutt's talk earlier, do the whole petroleum systems modeling, understand your uplift history, and be aware of these kinds of things. Now, I have to cover a lot of stuff in a short round, so I'm not going to get into a lot of the details with how you screen here. But generally, in tight gas, people are looking for 1.2 to 1.4 RO, and tight oil 0.9 to 1.2. Here's the danger. This is kerogen dependent. In the Barmer Basin, the northern part of the basin has a source rock which will not generate gas unless it's cracked. So you're not going to get a gas play in the northern part of the Barmer Basin. The southern part of the basin, the kinetics change and you get a gas play. Tight oil plays the same way. This is a 0.9 to 1.2 RO. That's a rule of thumb. In the northern part of the Barmer Basin, the algal-rich source rocks there mature at 0.5 RO. So this is something you have to be aware of in your kinetics. You want porosity, you want brittleness, so you can land your well somewhere where you can actually get a proper frac in it, and you have to know how to design that frac. You can map oil in place and gas in place from logs, and that's something you want to be able to do. You need to know your natural fracture orientation, overpressures, and the big dog in the room down here, what's your recovery factor? And that may be a function of your drilling and fracking history. So these are not easy plays to screen properly, and I think Udi's talk, which comes after mine, actually will show a proper screening technique. Now, what I wanted to do was get away from those basics, which I think people kind of know, and look at where are the unconventional plays in the world today. Well, they've expanded out of North America. This is where they started. They've gone into the Vaca Muerta in Argentina. I'm going to show you some examples here in Saudi Arabia and Iran. We're going to look at the Basins up here in West Siberia and some plays in China. So the unconventionals are rapidly going global. And if you look at a creaming curve, now these are rough numbers of potential resource. Somewhere between 2005 and 2010, the horizontal drilling and fracking really took off in the United States and North America and Canada. And that's where you see this big jump in the creaming curve. Now, it looks like it's flattening here, but it's not. This is just that we don't have good estimated reserves here. I'll give you an example. Jafira Basin has about 5.8 TCF booked for unconventionals in Saudi Arabia, but the resource is 270 TCF, and I'll show you that laterally. So this is only going to rise. We're going to see this curve continue to go like this through time. We're awash in unconventional hydrocarbons. Now, I want to go back to how this all started. Now, I'll go to Pete Matusik here in the Denver Basin. I knew him when I first came to work at Amoco. I came in about 10 years after he discovered the Wattenberg field. I love this story. he was mapping the basin, and he noticed by looking at DSTs that as you came toward the heart of the basin here, the Denver Basin, that the water production dropped off and you started getting more and more gas. And then down here in the bottom of the basin, he found about 12 wells that looked like they had bypass gas in them. And there were a few tests, but they didn't produce any water. And without knowing anything about the trap, he drew a line around these wells and then went back into Amoco. The Amoco office was right here. He went back into the Amoco guys and said, I think I have a TCF of gas in the bottom of the basin here. And they said, well, what's a trap? He says, I don't know, but I think it's down there. And they said, oh, so you're telling me in the bottom of the basin in a syncline, you've got a TCF of gas and it's almost underneath the building. We're looking around the world for TCFs of gas, and you're telling me it's underneath the building? He said, yes. So they threw him out of committee for 2 years. They thought he was crazy. He finally convinced them to go in and try hydraulic fracturing, which was a new technique. And the result of that was he proved up 1 trillion cubic feet of gas. So at the age of, in his early 30s, he became a legend within Amoco. What's interesting here is that was an out-of-the-box thinking, and we still have to use that today looking for hydrocarbons. It's really important for us to not put limits on what we think is going to work in an unconventional realm, and I'll get to that later. But the bottom line is, this field now has 40,000 wells in it. The trap is still not really well known, although it does appear to be a temperature-enhanced trap. This is the Colorado mineral belt here. It's a Precambrian basement anomaly that has gold and silver mines all along with this direction. And the temperature anomaly, where the temperature gradient is high, you've got all these productive wells. Now, generally, if it's 36.4 C per kilometer, that's where you're going to get the production. The trend does not match the structural geology. It matches the paleo geothermal gradients of the big Colorado mineral belt lineament going through here. So this field was found with well control. It wasn't found with maturation modeling. It was found with looking at logs, and the rest of the fields, now they're doing the maturation modeling and saying, oh yeah, this makes sense, but that's kind of after the fact. What's important here is there's now about 10 billion barrels of recovery in here and 40,000 wells. Thermal anomalies are important, and you've got them in Rava, you got them important to the Cambay. So when you're going through those old well reports out here, looking for the thermal anomalies is really an important screening tool to use in a place like India. The really interesting thing here is how the horizontal drilling is kicked off since 2010. Look at the footage drilled by horizontal wells. What's important here now is that they're getting these wells down 10,000-foot laterals. Some of them are being drilled in 2 days. I couldn't drill a well like that in 2 weeks when I started in the company back in 1980. So tremendous advance in drilling technology. Now let's shift to the Bakken Formation because it's another thermal anomaly. This play was defined in 1978 by Fred Meisner. He noted that there were high resistivity shales, which he said the high resistivity is due to oil. He made a map of it, and he says, I think there's an oil play in the Bakken. Well, everybody thought he was crazy. So somewhere about 15 years later, people started testing horizontal wells out here, but they didn't get it right. They had the wrong zone targeted. Well, if you look at Fred Meisner's map here and you look at the Bakken production today, he nailed it. 1978, without doing maturation modeling, just looking at the well logs, he got the play outline correct. But it took over 20 years to recognize the landing zone. Everybody was drilling into the shales. The shales are collapsing. The landing zone was the middle siltstone, and that's what's driving this. Now, again, this is a basin that's very hard to do a maturation map on if you're trying to do it with some model like Trinity or Petramod, because the maturation follows the aeromagnetic anomaly at depth. It does not follow the structural contours. So this is another heat flow anomaly. One thing that was recognized early with, there's a lot of rock eval data here. was this HI wall, which is HI decreases rapidly, and that's the edge of the productive basin. And just outside of this is the biggest pool, but you can actually map with HI or Tmax the limits of the Bakken play and find new prospects. Now, I want to jump to the biggest play in the world, and this one's been getting done since the 1960s. It's the West Siberian Basin. This is a Bashanov maturation map. Look at the productive area, 2.2 million square kilometers. It's a vast cratonic basin, simple structure. It's been producing since the 60s in one of the fields down here, Salim, from these radiolarian Bashanites. There are also injectites and a layer called the Achimov in here, which is a primary play fairway. And you've got this is many potential analogs in India of this particular play. So here's the source rock down here. Here are the cliniforms in the Cretaceous, and there are slope turbidites coming off these cliniforms and pounding their way down slope, mixing it up into the Bashanov. They're getting intimately linked to it. When the early maturation takes place, these things fill up with oil and gas, and as maturation continues, they may they get tighter and tighter rocks, so they end up being actually pretty poor reservoirs. But they have hydrocarbons in them, independent of the capillary pressure. And this is a big play. One of the estimates in here was the Achimov tight play may have 2P reserves of 27 billion barrels of oil just down in this area alone in over 100 different known accumulations. So it's a big play. Also in the tight realm, Nezhdev-Sinonian was discovered up here, added about 2.7 billion barrels in pay that was behind pipe for like 30 years. So these are good analogs for any kind of a deltaic platform across India where you have turbidites associated with it going into mature source rocks. Now, a carbonate analog to the Bashanov and Achimov play right here is the Vaca Muerta down in the basins of South America, down here, Nucan Basin. And look at the oil production coming up here, up to 120,000 barrels of oil per day. It's in all sorts of carbonate-rich turbidites and deposits that are interbedded with the mature source rock here, and that's a really good analog to what's going on in West Siberia. So it's just in a carbonate realm. My point is, you get these brittle zones bedded into the mature source rock. That's a good thing. Now, we want to look at a little bit in the Delaware Basin. This is where the big production's coming out of the U.S. The Delaware's a deep basin right here. The carbonate facies go from carbonate breccias and shelf carbonates up here to carbonate breccias, and then increasingly distal turbidites this direction, again, stacked at many, many different layers. In the 50s and 70s, these wells were completed with vertical well bores and vertical fracs, but increasingly the well bores are going horizontal, and as I mentioned, up to 18,000 feet laterals to make this basin work. And look what it's done for the West Texas Basin. This is the biggest unconventional play in the United States. It's massive. It's going to be going on for years. But it's a good example of what you can find, again, in the turbidite realm, wrapped up in mature source rocks. Now, shifting gears a little bit to Oman, there was a conventional field up here on the Makaram High, which had some poor gas wells in it. They were tight. These are Cambrian wells, but they were producing gas well beyond the limits of what the structural closure looked like. As BP began to look down the flank, they discovered that there were massive piles of these fluvial sandstones down the flank. They couldn't find any water in it. They don't really understand the trap very well. But this went from being an uneconomic small gas field to a 25 plus TCF unconventional tight gas field. Again, found with production data and good geoscience. And the trap is still not that well understood. Jumping to China and looking at the Ordos Basin, they used to think this basin, which is sourced by coal gas directly below these reservoirs, and it's intimately linked. These are they used to think this basin had about 18 TCF from all traps. Now they think the basin's got about 145 TCF basin potential. So what looks small became big with infill drilling, and that's another theme you see over and over again. The closer, most densely drilled these things get, the more the reserves come forward. Got a really interesting one here in Iran. They announced
I would just like to remind for the time. That's just a gentle reminder.
We'll wrap up right here. Namavaran is probably a very big tight oil play, and in the Jafurah, we've got a new pool that's coming in here. And I just wanted to point out that the Barmer Basin is very different. It's narrower. It's about a third of the size, but again, these plays are working and they're big resources. Now, one of the things that's called an unconventional are these big conglomerates up in the Mahu area. They're not really unconventional because they're 1 to 2 kilometers above the mature source rock. But there are many plays around India of flank type conglomerates, which might be analogous to this. And you can look at the top later. I'm going to wrap this up by saying the examples I've shown is that we've got tremendous volumes of future hydrocarbons in these tight resources. But a lot of India's plays are in rifts, and you're on the cutting edge because these are enormously complicated. These are not the low cratonic ramp things where you have facies that stay fairly consistent over very large areas. Really, in India, you're on the cutting edge of trying to unravel the plays inside rift sequences. So the government here really needs to do a lot to encourage unconventional plays, particularly the ones in these rifts, because every well that goes down in a rift is going to pick a different landing zone or have the landing zone change. So I'm going to wrap this up saying the top only touches the surface. Obviously, if you want to look for new big unconventional plays, go in the super basins. And the rifts are an enigma and are going to take a lot more work to understand. Okay, that's it. Any questions?
Thank you, Mr. Dolson. If there are any questions, we can take them. Otherwise, we'll move on to the next presentation. Thank you so much. We'll be summing up later on by the session chair. Namaskar, good afternoon from Upstream ahead, India. The next presentation is going to be on gas hydrates, the resources and opportunities as well as challenges thereof in India. And this is going to be presented by Dr. Timothy Collett. Dr. Collett has been a leading geologist in the U.S. Geological Survey, USGS, since 1983, and has been the project chief for the Energy Resources Program, funded gas hydrate research efforts for the USGS. There's a lot of things and a lot of developments which have come in for gas hydrates. To have an updated window into the exploration as well as eventual exploitation of gas hydrates, I would like to hand over the presentation to Dr. Timothy S. Collett. Thank you, sir.
Thank you. Yeah, thank you very much. First off, I'd like to thank the organizers for the opportunity to present to the summit today on India gas hydrate resource opportunities and challenges, and particularly with gas hydrates. We'll try to look at from an Indian perspective, but also from a world perspective, where we'll try to understand hydrate resources more globally from that perspective. How we're going to do that today is with the following outline. We'll first start off with a discussion of what are gas hydrates, And this basically goes through kind of the history of gas hydrates and some of our discoveries, but in particular, what are the reasons we're interested in hydrates as a resource? We'll look at gas hydrate production R&D summary, particularly looking at concepts of production testing from other sites across the world. And then we'll focus the main body of the presentation on the India situation under the Natural Gas Hydrate Program of India, or NGHP, particularly focusing on the NGHP 01 and then the 02 expedition from 2015. And then we'll talk a little bit about the future and some considerations of looking at production testing. One of the most important considerations of hydrates are looking at, beyond their geologic occurrences, understanding the technology required to produce them themselves, and finally move on to the resource challenges. What are basically the resource challenges relative to mainly production? So again, before we really start, I need to really acknowledge the contribution of the Indian National Gas Hydrate Program, both to our understanding of hydrates in India, but up throughout the world. This has been fundamentally one of the more important gas hydrate programs we have seen ever. And particularly with the contributions, what we have seen from led by the Ministry of Oil and Petroleum and Natural Gas and forming the NGHP effort, but particularly also DGH, the Director General of Hydrocarbon, and program managing the NGHP effort. And it also, the NGHP, and particularly DGH, is our relationship, what maintains our USGS partnerships, where we're able to conduct research together on gas hydrate, both in India and throughout the world. Again, gas hydrates are an ice-like mixture of gas and water. They're basically a solid structure. They occur under a limited range of pressure and temperature conditions. And in this case, we see a hydrate cage or water molecule structure, what encapsulates single gas molecules. These occur under a limited range of pressure temperature conditions that are found in the deep marine environment and, of course, in the high Arctic environment associated with permafrost. Most of the issues associated with the resource potential of hydrates deals with its storage capacity. A hydrate, being a solid, stores a very large volume of gas per unit volume. So you have a yield of about 180 cubic feet or 180 cubic meters from a given cubic meter or foot of gas hydrate at standard temperature and pressure. Again, occurring in limited regions of the Arctic and deep marine environments. And a little bit of the history, and one of the most interesting aspects, hydrates were only considered to exist. That is the pressure temperature conditions by Yuri Makagan in 1965 from his work in Siberia. And so when you think of gas hydrates as a potential resource or just as a scientific topic, it's still a relatively new science. And we're just seeing here different structures of gas hydrates. It's very important to highlight that the occurrence of hydrates are caused by the interaction of the gas molecule in the cage or the water cage when it encapsulates them under a limited range of pressures and temperatures. When we look at gas hydrates, it's important to kind of compare and contrast these with other conventionals and unconventional resources. In this resource pyramid for all gases, we have placed gas hydrates, which show basically the volumetric component of the in-place volume of gas or carbon associated with hydrates, and comparing those to other conventional resources, unconventionals, and also most recently the emergence of things, of course, like deep shales and others. So we see in a resource pyramid like this, the area of the pyramid shows the relative volume of those resources, one to the other, but also shows the evolution through time of these resources, with hydrates still having no production other than limited production tests would have been conducted, and we'll talk a little bit more about that. So it's very important when you hear about hydrates, you always hear about this vast potential, but it's also important to understand how the hydrates are distributed, to understand their actual resource potential. Here's a gas hydrate resource pyramid. Again, the concept is the pyramid represents all the gas contained within hydrates throughout the world. At the top of the pyramid, there's estimated most of the gas hydrates, what we feel are resource viable, that is within sand reservoirs where you have porosity that allows for the hydrates to become concentrated, but it also allows the development of production technology to actually produce those hydrates. However, most of the resource pyramid for hydrates are made up of hydrates that are disseminated at low concentrations in muds, and it should not be considered a resource. So it's very important when we talk about gas hydrates as a resource is that we're going to focus primarily at the top of the pyramid at gas hydrate and sand reservoirs. So again, this comparison, even though interesting, it's very important to indicate that the actual potential resource of hydrates is very large still, but mainly the top of these pyramids and sand reservoirs. To take that explanation or discussion further, Art Johnson in 2011 with Hydrate International worked through an assessment of in-place gas hydrates within sand reservoirs globally. And for particularly our discussion today, we see in India, Art at that time estimated about 933 trillion cubic feet of gas. So a very large volume of gas in place. So this is very critical when we talk about hydrates. You'll hear us, we usually talk about in-place resources. The only place that we've ever conducted technical recoverable resource assessments are in places like Alaska, where the data was relevant or allowed us to be able to do that. So again, focusing on sand reservoirs, the volume of in-place resources are moving along to the direction of technical recoverable and ultimately reserves, but we're still in the very early phases of understanding hydrates as a resource and are primarily a scientific issue at this time. When we look at gas hydrates, this map here shows our toolbox. And what I mean by that, these are the sites that actually have been drilled and characterized for the geologic occurrence of hydrates. And the projects that are shown in red are actual production tests, or are going to be the focus of a large portion of our discussion today. So we see our projects on the North Slope of Alaska, where we've had 3 main production testing programs, including an extended production test that's getting underway here in about 6 months from now. We also see the first geoscience studies of gas hydrates, where the ocean drilling program, Leg 164, conducted in 1995. So this map would have been empty. There would have been no drilling projects or research projects dealing with gas hydrates. They all have been since 1995. We see other ocean drilling programs where geoscience projects. We also see our efforts in the Gulf of Mexico, particularly a joint industry project led by Chevron, and also more recent University of Texas projects to look at a combination of the geologic currents, hazards, and resource potential in the Gulf of Mexico. To take this story further, one of the most important first projects in gas hydrates anywhere in the world was a large partnership, including components of DGH from India in 1998 and 2002, and more recently the production test of 2007 and 8 at the Malik site in the Mackenzie Delta. Probably particularly most interesting for us today is the marine gas hydrate research efforts. The Japanese program has been leading the way since about 1995 also, with 2 production tests, one conducted in 2013 and another test conducted in 2017. And also we see a very large directed effort on the North Slope of the South China Sea, with 6 geoscience expeditions have been completed over the last 8 years and 2 production tests, including 2017 and 2019. We also see in the Yulong Basin of the eastern margin of Korea 2 geoscience expeditions conducted looking at the resource potential of hydrates. Both of these around 2011 and 2014. But most important for our discussions today is focusing on the Indian expeditions of NGHP of 01, what was in 2006, and Expedition 02, what was in 2015. Just to add to that map, this is a timeline which shows the same information. We'll go through this relatively quickly, but we see the deep marine projects, permafrost projects, any project shown with circles are geoscience projects, any project shown with squares are projects that dealt with production testing. And we'll talk more about the Malik projects, the Mount Elbert and Ignatsukumi projects in Alaska, and the 2 Nakai Trough tests and the South China Sea tests themselves. So let's move on and talk about the production aspect of gas hydrates. One of the most important aspects is talking about the geologic nature of hydrates, the geologic controls, the systems type approach, what we use also for hydrates. But now we want to look particularly at the production technology. To produce gas hydrates, this is a gas hydrate stability diagram. Anywhere in the pressure temperature realm in the green area. So this is depth in meters, temperature is 0 degrees axis. Again, hydrates occur well above the freezing point of water because of this interaction of the gas molecule itself within the cage. And to produce hydrates, we basically have to move the reservoir setting here of the star across the stability boundary. How we do that is by in-place depressurizing. This is a conventional well. So basically drilling a conventional well, drawing down the head on that well, and actually trying to produce the hydrates by depressurization. The next one, of course, is heating. Of course, some combination of those, but also injecting an inhibitor. So you can imagine anything that changes the pressure temperature realm, but also if you inject a chemical like salt, if you do methanol and other chemicals, you will dissociate hydrates in that way too. What became an interesting project with a lot of appeal in 2014 was the fact that you could inject CO2 into a hydrate-bearing reservoir and displace the methane and encapsulate or sequester the CO2 itself. So you had a production technology, including a sequestration technology. It's still a study what's being looked at in detail about rate dependencies. And all of these have certain interdependencies and rate considerations. So again, our main focus for production testing and also reservoir exploration is looking at sand reservoirs where we can complete wells in for depressurization testing. This is the list, much like the previous map, what we were looking at is all the history of production testing of gas hydrates. And the thing I wanted to focus on was just a couple aspects. The first onshore of production testing of hydrates was only a 6-day test in the Mackenzie Delta of northern Canada permafrost setting. So really an experiment. And these experiments were mainly conducted to calibrate production modeling. So we had computer simulators. What we've been using as our primary focus to predict the response of gas hydrates to depressurization. We see the next largest project, the ConocoPhillips project for the 25-day test. And then we see the first marine gas hydrate test being 6 days only and 60 days for one of the longest ones in China. And again, 2 tests being conducted in the Nankai Trough in 2017 of 10 and 30 days. And I don't note it here, but approximately a slightly over 60-day long test in the South China Sea. Again, all looking at depressurization technology. So what's very important when you look at this history is the fact that these have been short duration experiments, and they were designed intentionally that way to basically calibrate production models themselves. So when we look at these results, they're not overly appealing when you look at the overall field tests themselves. But again, it's very critical to note the intent of these tests was not to look at demonstration or production rates, but to look at the experiment, the actual response of the hydrates. So approximately 60,000 and 940,000 cubic feet of gas per day from the offshore test, and 60 is kind of 2 of the peak values. But one of the things we've done, of course, with our production simulators, we have tried to predict production rates over the next 20 to 30 years of the life of a well. We see peak production rates who actually climbed from these initial rates up to about 4 million standard cubic feet of gas per day for some of the onshore settings. But we see much higher production rates, particularly because of the warmer reservoirs in the offshore settings. And also when we start considering horizontal wells and other technology. So the goal would be is to actually evaluate this disconnect right now between the field tests would have been limited in scope and looking at the production modeling results. The next aspect of this, we like to turn our attention to India. The NGHP-01 and 02 expedition both had extensive geophysical site review efforts and prospecting efforts before the actual drilling expeditions, much like any conventional oil and gas exploration effort. Planning and execution of NGHP-01 and 02. Again, these were extensive expeditions. What we see here in the red dots are the projects were drilled in 2005, both the west coast and east coast of India, including the Christian Godavari and Mohapatra, and also in the Andaman areas themselves. With the results of NGHP-01, we moved on to NGHP-02 in a series of exploration phases, mainly conducted by ONGC and their geoscience staff, to be able to look at a series of 26 prospects that were drilled during the NGHP-02 expedition, both in the Christian Godavari Basin, but also in Mohapatra. Also, the ongoing work is operational planning, what's mainly focused on the potential of doing production testing for hydrates in the offshore of India. I'll go through this very quickly. It's a long text slide, but the results of NGHP-02, the most significant was we had the presence of reservoir quality sands. Again, the primary target for gas hydrates as a producible resource is to focus on sand reservoirs. What was very important from NGHP-01 to 02 expedition was the appreciation of the reservoir systems and the bypass nature of the deepwater depositional system in the Christian Godavari Basin. We're able to identify deep water, thick sand depositional systems in both basins. We're able to discover in what was referred to as Area C. I'll go back again. Area C here is in the southern part of the Christian Godavari, and the very northern extent up into the Area B and then Area E. So the main target areas of Area C and B was important to highlight in this discussion. In Area C, we had very extensive deepwater depositional interconnected systems from toe of the slope to distal fan systems. We had thick hydrate discoveries of over 50-meter thick channel levee systems fully saturated with gas hydrates. And in the Area B, it was a different type of play. We're looking at a large toe thrust anticlinal feature where we were looking at a distinct anticlinal feature where the hydrates occurring much like a conventional field at the crest of the structure themselves. And again, Area B and C represent really world-class gas hydrate accumulation, some of the thickest, most extensive reservoirs with hydrates that we've discovered anywhere in the world, and extremely suitable for consideration of production testing. Just to want to highlight several of these reservoirs. In the Area C area for gas hydrate examination, we ended up drilling a series of 10 test sites and coring a series of 5 of those, included a high standing channel system, channel levee system, and a distal fan system shown here as 7, 8, 9, and 10 will correlate to the map here. The hydrate bearing reservoirs are shown here in blue. We see basically a high standing channels, very thick channel levee systems. Particularly what we see here at site 8 and 9 is up to 50-meter thick hydrate bearing reservoir sand systems and levee systems and channels. And finally, in the very distal part of the system itself, we see these distal turbidite sands on thicknesses of up to 5 to 6 meter thick, but very thick in total cumulative thickness and others. So it's completely interconnected depositional system with hydrates occurring across the margin and into the deep water environment. Again, these are depths, a little over 2,000 meter depth, water depth. So we're pretty much at the toe of the slope and beyond. The next site, as I mentioned, is Area B.
Yes,
Area B.
Reminder for time, 2 minutes more, please.
Okay, thank you. Is a tightly folded anticlinal structure, a high amplitude feature at the top of the crest of the structure. When we were able to drill that structure, what we see is a very thick hydrate accumulation with up to about 20 meter thicks of hydrates. Again, much like any other resource, we look at amplitude maps because of the high velocity nature of the hydrate structure accumulation itself. The consideration for future production testing under the NGHP structure, we had an advisory committee and the members concluded the following members in 2019 made the following recommendations. What basically concur of looking at the geologic data from both expeditions, consideration for additional sites, what additional data would be needed to move ahead with production testing, and finally, what is the design of these tests themselves, and finally, the operational plans themselves, much like you would see in any other conventional resource evaluation and characterization. I have about 3 more slides, but just deal with the challenges. This slide itself is from our colleagues at Japan, but basically show the status of our knowledge of these previous production tests, our ability to look at these short-term duration tests, and the need now for long-term production testing to understand the trends of these different predictive models. And finally, I just wanted to end with these two slides, which show some of the issues about the productivity of hydrates. And one of the concerns, of course, is hydrates are mainly water. So you have a high production of water associated with hydrate production. You have other control issues. One of the only models what we've done was actually based on an India model where we actually looked at production rates from single well modeling efforts and looked at depressurization concepts of 6 well clusters and water depths of a little over 5,000 feet. And what we're able to look at in benchmarking these with conventional production, the same geologic settings, and looking at production rates on the order of 10 to 20 million standard cubic feet of gas per day as a target, we could look at economic returns, what made hydrates a viable resource relative to a benchmark of the conventional resource in those same settings. So these are very early model-based predictions on these short-term tests. Finally, my conclusions. The challenge for gas hydrates as we move forward is move from these in-place estimates to move to both technical recoverable and hopefully eventually reserve estimates. The need for scientific production and mechanical testing to further evaluate our actual and development of our computer models for both mechanical and environmental testing. And finally, really looking into the future. And really very soon, we think be moving beyond the scientific test to demonstration test, where we can actually look at maximum rates of productions and others. So again, I thank you for this opportunity and hopefully can answer questions later today in the forum.
Thank you, Dr. Collett, for giving such a lucid presentation on the entire gas hydrate exploration and production gamut.
Thank you.
We have been after the gas hydrates for some time now, so hopefully in the future that becomes an additional source of energy for all of us. So waiting for any queries and questions. In case there are any queries, please do put it up.
And I'll watch the chat through rest of your forum.
Yes,
too,
I've already checked the chat, and at present I cannot see any query come up on the chat box. So from the upstream ahead, thank you so much, Dr. Collett. Might be there'll be people putting in queries later on, so that can be forwarded to you.
Sure.
So thank you so much for your wonderful presentation. So I think we can move on to the third presentation. Namaskar to everyone again. We move on to the third presentation for the session, which is on the E&P from shale play, the global scenario, Indian context, and progress in the Barmer Basin. And this very interesting presentation would be presented by Dr. Utpalendu Kuila, who is a senior petrophysicist with the Cairn Oil and Gas, Vedantal Limited. He'd be giving his presentation, taking the case study from Barmer Basin, dealing with the exploration as well as production aspects from a shale play, as well what is the current global scenario and what context it has for our Indian basin. So it is over to you, Dr. Kuila. Waiting for the presentation from your side. I think there are a lot of interesting things we are going to learn today.
Thank you, Sushma ji. Good afternoon, respected delegates. So John already introduced this slide, so I will just go fast. On this particular one is on what is the motivation for today's talk, and we are all aware of the impact that the shale and unconventional plays has done in the US and the oil industry as a whole in the last 2 decades. It has not only debunked the peak oil theory, arrested the decline, and within just 2 years, the growth, and if you see the rate of increase, it has become one of the largest oil producers and eventually the net exporter of oil. Now the big question is, can we replicate the impact of the shale revolution in Indian oil production future, particularly to meet the gap between the internal demands which we meet by net imports with the production. So that's what we are going to address today, and this is the agenda. So before going into the details, we like to have a definition, because there are a lot of terms that kind of floats in: shale plays, unconventional plays, tight gas plays. And we will kind of restrict to our definition, which I called unconventional continuous resource play, or the UCR play. John already showed examples from North America, but what I will do, repeat some of those slides, some of those contexts, and to understand what it means to design an exploration strategy for the plays that we are doing, because understanding the characteristics of the rock is required. What we are planning for the way ahead? What should be our exploration strategy? Whether one well will be sufficient, or do we have to drill multiple wells to kind of, before we know how potential those things are? So that's what I say as learnings from North America. And then we will go to the Indian play potential for the shale plays or the UCR plays. And we will go very briefly on Barmer Basin, the work that has been done internally in Vedanta and Cairn Oil and Gas Vedanta Limited, the exploration workflow. And then I will conclude with the way forward. So there are multiple terms that is used in the industry. Mostly there is overlapping definitions. Shale play, tight play, low permeability play. But what we want to understand is primarily from an exploration perspective is on a petroleum system model. And that's why we use the term continuous resource play. So we have looked into these pictures about hydrocarbon accumulations from Cairn and Polastro 2001. This is very common. But the way we define the continuous resource play is the plays which is below the maturity window. So this is or the play where the shale source rock has geologically starting to produce oil or gas. One of the misconceptions is that it's essentially shale, but one we have to keep in mind that the definition is it's in between or near a mature source rock, but the producing interval did not necessarily be shale. From petroleum system perspective, the hydrocarbon is still in the primary migration stage, and the traps are not buoyancy control, so it has no trap geometries. And one of the concerns that we always hear is that whether a play is conventional or unconventional, one thing we have to remember that in nature, the geologic process are continuous and it's continuously going on. So they doesn't care whether it's oil and gas. It's our human is to divide the observations, and so that we can club it into a scientific hierarchy and club it between whether it's a conventional and unconventional. So and in reality, what's happened is these are two end members that kind of defines how hydrocarbon can occur in geologic plays. Why the definition is important, because this is why this is what affects how we want to map the target, how do we want to assess the chance, what are the data we have to analyze, and particularly our strategies for the entire value chain. So we use the definition to make our strategy. The hydrocarbon occurrence is happening in the natural scale. And I always use this analogy of pressure cooker cooking to explain unconventional resource play. We can think of our source rock, organic matter deposition in a basin, as we use raw food to cook in a pressure cooker. As we heat the cooker, the fat is rendered from our food, which is our kerosene to the oil conversion. And in this process, it increases the internal pressures due to the low permeability of the source rock. The fat or the oil that is coming from the food redistributes in the pressure chamber. a process that we called primary migration. While the cooking is continuous, there is periodic whistling, which we can relate to periodic hydraulic fracturing of the main source rock, a process that we called that process that leads to the secondary migration. So the objective of unconventional resource play is to go into that kitchen, the oil that has been cooked, use energy, because these are extremely low permeability rocks, use energy to extract this oil out of the ground. So that's pretty much it from and what's an unconventional resource play is. We looked into, in the previous presentation, we looked into the global occurrences of plays. The most commercial play that we will say will be the North American example. Argentina has also been, the Mohapatra play has come into the world map. China, there has been a lot of data, there has been a lot of activity, but because information is not that readily available on the production behaviors from the Chinese basin, and the upcoming emerging commercial plays are Australia and Saudi Arabia, as John Dolson has already shown. There are different, however, potential that has been recognized rest of the world, like Poland, in South Africa, Karoo, but none of them has in the commercial state. We looked into North America because in the last 2 decades, they had decoded the production thing of, we understand the occurrence of this hydrocarbon. The main thing is how can we produce that hydrocarbon? And over the last 2 decades, North American play has achieved operational efficiency that was never seen before. And what we will do in the next few slides is look into the learnings from the North America and understand why these are difficult plays. So one of the things we will look into is the chance of success. One of the attractive thing of unconventional that people think that unconventional players have very high geological chance of success. You can go drill practically anywhere within the maturity window and encounter mobile hydrocarbon. But it does not reduce the commercial risk relative to conventional plays. And the reason I say that, this is the map for the lower 38 and with all the play maps that has been tested till then. So more than 50 maps has been tested, out of which 12, about 25% of those plays have been commercially developed. And even in the first order of business is to focus the right play in the right basin. But even in the productive basin, when you go for commercial fairway, it is only a fraction of the basin. It's not the entire basin. So as you can see, the example here in Marcellus, it's about 25% of the entire Appalachian basin is what's commercially productive. So when you see from a chance of success from a commercial end, it's actually not very less riskier than a conventional play. But the difficulty here is the risk translates to the later stage of the project. So for a conventional well, the biggest risk is to drilling dry wells, but you will drill 1 or 2 dry wells and you will get out of this project. But for unconventional, you have to drill a lot of number of wells, crack the code of extracting that before you can understand whether that hydrocarbon can be produced economically or not. And that's what we see in the figure. So there are, this is data from Wood Mackenzie that shows the period from 2004 to 2013 and how much value it has created. So you can see some of the major companies, that is, it has failed to deliver positive development value, even if there is hydrocarbon in that place. So, and why this is the scenario, why it is, if the hydrocarbon is there, why it is very difficult to get. And part of the reason, and main of the reason is the high variability in the well performance. What we see is a figure, this is the Bakken example. These are production numbers, per well production numbers of horizontal well in MBOE. So as you can see, there are different productive zones within the Bakken. But if you look into each of the sub-segments, which is color-coded by the map here, you see a huge distribution in where you are. So most of the wells are actually on the lower side. It's in the log normal distribution, and the few percentile wells that is actually driving that entire project in. This level of variance becomes very difficult to predict for a future development project. And this is variation in a basin scale. You are going in a field, and this is about 5 kilometer scale bar, and you can see whether there are sweet spot. But if you compare wells from here and wells from here, the production, and this is an example for Barnett, is tenfold. So what it tells us that if we drill 1 or 2 wells, it will not be enough to judge the entire scenario. And offset well performance is not a reliable predictor of undrilled performance. We should have some perseverance, and inference should be drawn from statistically significant data. We should have a good population of production wells before we can conclude whether that play can be productive or not. What makes it more difficult is the number of parameters that you have to pay in conventional tools, but in unconventional tools, the parameters are huge. You not only are dealing with multiple subsurface parameters like organic thickness, basin models, you have the tools that you control on the completion design, the lateral lengths and the frac lengths, and these large number of parameters needs to appraise. And that's what leads to a long learning curve for those unconventional. We need to stay into a curve till we understand those. And then probably initially some of those, there will be significant numbers of uneconomic producers. So it needs to have a readily disciplined approach, look into not in a well by well basis, but on a statistically significant data. It has to be continuously done because a start and stop development program is not conducive to learning. And we need a fiscal regime that can support this kind of plan, do, measure, learn, repeat cycle to actually take those hydrocarbons to the ground. And the fourth reason is the decline. This is the figure on the left shows the declines on the different basins, and you can see most of the North American shale play, and this is only gas production, declines 80% in the first 3 years. So what we have to do to maintain, we have to continuously drill. This is an example from EOG. They drilled 7 exploration wells in 2009, but if you see the number of wells they have drilled, from 2009, they started with 7. See the number of wells they have drilled per year, up to 500 wells within a total acreage of 2,000 square kilometer to get to a production of 230K BOPD, and then kind of drilling 300. This is where they optimize the drilling. So you need to continuously drill to maintain the plateau of the peak. And one interesting thing is the cost. So the laterals, they used to drill with $7.2 million in 2012. They reduced it to 4.4, and that's where the economic and manufacturing scale that you hear of comes in. So if we look into the Indian shale potential, the two understandings that we have is from EIA and USGS. One thing I would like to highlight is the difference in the estimated recoverable values, and these are very basic, very preliminary estimates of the reserves that we have. What is the need of ours is an internal effort to estimate what kind of reserves that we have, including all the major participants in the industries and the government. One important thing to note that Barme Basin was never considered in some of those basins. So even if in this the Rajasthan that was considered was only Bikaner, Nagaur and Jaisalmer Basin, and there is no evolution that is present. So what I will do in the next few slides, take you through what we understand on the example of Barmer Basin, how it is different, and where we are in the shale gas program. So prima facie, Barmer Basin has a world-class source rock. It's a rift with an algal types. Look into the hydrogen index of about 9,000. We have the optimal oil and gas as evidenced by the conventional discoveries that is there. This is the maturity map. The red indicates gas windows. The green indicates oil windows. And these are some numbers that was calculated from basin model. The numbers are in billion of barrels, and it is more than actually 10. So whatever number is there is a large storage that is potential within that. So once we started that observations, what we did is we compared this Barmer Basin to the North American Shale System to understand whether exploring new shale is feasible or not. What we see, the major difference, whether the source rock is a very good news, there are some uncertainties. First of all, rift basin, there is massive lithofacies change. The landing zones will be completely different. Actually, you can see different kind of shale plays that you see in US is actually present within this small Barmer area. It has limited aerial extent, but thicker sections. So typical thicknesses in US plays about, except for the Permian, which is a thicker one, is about 100, as an average of 100 meters. But here the thicknesses goes up to 800 meters. There are some uncertainties about the lacustrine corrosions. And one of the things is we do not have penetration in the target wells. So as John has shown that some of the unconventional plays was actually based on the extensive drilling that US has done and relooking into the data. Barmer Basin is, even if it has 2 decades of conventional history, most of the wells are drilled on the structural highs. So this is the maturity map, and as you can see, there is very little understanding of what's happening in the kitchen. So most of them are model based. So in this particular context, what we did is, if we have to, there is a prima facie evidence of a good source rock. So if we have to test, where should we target our exploration? The first is we used a play-based approach to delineate the most prospective target areas, and then estimate the resource volume by tank method. So I will skip this part for a detailed for a play-based exploration, play-based workflow. So what this play-based workflow is similar to conventional workflow, but the fundamental philosophy of a play-based is to gather, organize, and synthesize all pertinent data into a form of map which can help us strategize and subdivide to focus on the exploration strategy. So what we have did is we integrated all the available data and divided into a play segment and sub-play segment. And this is how we divide the entire understanding in terms of hydrocarbons and of fault reservoir systems. So this is how we integrated thickness map, geochemical understanding to find out which will be the oil areas and the gas areas. We identified about 391 square kilometer of oil within the RJON. It's part of the Barmer Basin, not entire Barmer Basin that was been evaluated. We looked into integration of code data with seismic phases, and one of the key challenge in Barmer Basin is the rift settings. So you have settings where you have organic rich cells, completely like Eagle Ford type, and then when you go into the into some of the other subbasins, you see turbidite mixed with that. What it relates is your landing zones will be completely different. The strategies, the storage behavior is completely different. So for one of the example, we looked into it with the US analog. So this is one of the example from the Northern Basin. This is where the porcellanites or the porcellanitic mud rocks goes into the window. And we compared that with the Eagle Ford plate to understand whether it can be a source rock, what is the storage potential, we identified the kind of storage place it would have from the analog study and compared that with the data that we have on the structural height. So as you can see, the core is very similar to the Woodford cell, except the core is coming from a place which is thermally not mature. So finally, all those data was integrated and we divided this entire area into oil and gas plays. Then the oil areas was divided into sub plays, and we the sub play on the play segments, and the play segments is based on the analog. So we have like rock systems like Barnett, we have rock systems like Woodford, which is mostly chart and organic rich cells. And then we have hybrid turbidite interlayered model where we have like the Delaware Basin, the Green River Basin. So, and if we look into the gas, it's mostly on the turbidite plays. If we quickly look onto the numbers, we have about and this is part of the Barmer Basin, we have about 15 billion barrels of oil in place. And if we talk about the recoverable unrest, we have about 3.3 billion barrels of oil recoverable between oil and gas, 1 billion in oil and about 13.2 TCFE of gas that is estimated. We compared that with the other
just reminding you, Dr. Kuila, for the time.
Yes, this is my second last slide and I'll be concluding soon. What we looked into is a comparison of Barmer Basin with the other basins and the other activities our national oil companies is doing. What we have good is very brittle source rock with presence of siliceous mud rock. We have turbidites. The stress conditions is strike slip. So, and the biggest advantage is the kind of TOC that we are getting, 3 to 15% is very high. So that's where becomes Barmer Basin a very attractive shale play. What we need to do from here. So we are actually here. We have done the screening. What we have shown is area that is there. The next thing is we have to drill the horizontal pilot because all of them are right now models. It has to be proved by drilling a hole in the ground. For sales, we have to drill a vertical with a horizontal well because if you produce from a vertical well, given the permeabilities, you will not flow anything. So it becomes very imperative that you drill a horizontal well at the exploration stage itself, which is not very known of. Then once you go into the discover for hydrocarbon, it doesn't mean it will be automatically commercial. So we still have to crack the shale code. What kind of completions or frac things that needs to be done? That's a lot of investment, and to protect the investment, it has to be done in a very disciplined state-based approach. So for example, we drill the deliverability well to delineate the area from a production point. Then we do a demonstration phase where we do pad drilling and see whether that project is commercial or not. And then we go into a competitive, like a company-wide competitive level where we replicate that and reduce the cost into a modular development program. So it's not one development, it will probably combinations of multiple developments with each development projects looking into statistically significant wells. And then at end of each of those projects, we have to evaluate whether we are commercially reasonable or not. So this needs a long-term commitment. So that's what the challenge is there from the Indian context. We need a long-term investment and perseverance to crack specific shale codes. We do a lot of understanding from North American shales, but again, all shales are different and you need to have this local understanding. One of the things that needs is to facilitate technology from outside. The kind of frac rates that US right now use, we do not have that kind of horsepower or the drilling rigs that is there right now in India. So we need to, for the government and the whole needs to facilitate importing technologies so that the learnings can be directly applied in Barmer Basin. We look into data adequacy and knowledge sharing. There have been studies that is going in different companies, but we need platform like this, Upstream, where we can come, talk about the best practices, share data, and probably come up with a national potential map. We are still relying on EIA and USGS numbers for our national sale numbers. So this has to be extended for all the potential basins in India. And finally, the need of the hour is a very focused fiscal policy for shale play. And it has to have a long discussion between all the shareholders, between the government, the policymakers, the service providers, the companies that was doing those, to have a very focused fiscal policy. And I'll give you an example. There are a lot of policies that has come in, like for example, the UCS policies has incentivized unconventional in year tax, but then they have also imposed a 10% profit petroleum, which is counter. You are incentivizing other than kind of increasing the profit petroleum again. So it has to be very focused, understanding the kind of capital investment it's there and the risk that is there. So we come to this conclusion. I will not take slide. We have just gone. So the key message is it requires a plan, do, measure, repeat cycle approach. We need a fiscal regime that supports this kind of long-term investment and commitment. Barmer Basin is attractive, 956 MMBOE for oil play and 13.2 TCFE for gas play. And what we need are exploration wells, because these right now are models. And as they say, the proof of the pudding is in the eating. So we need to drill exploration wells to confirm that. And in this final slide, I just want to compare between cricket and a North American game, which is called baseball. In spite of similarities, you cannot make a game plan of baseball using the rules of cricket. So to play this North American game, we have to discuss and implement a fit for purpose game plan so that we can extract shale from these basins. With that, I would conclude my presentation. Thank you, and happy to take any questions.
Thank you, Dr. Kuila. Wonderful presentation, very structured. The way forward for shale gas, how we would go. Of course, Barmer being a very, very prolific hydrocarbon province. So adding on to all those reserves within the basin of any place would be, a big addition to our own indigenous oil and gas kitty. So I was looking at the chat box. We right now we do not have any queries from anyone. So once again, thanking you. And then we move on to the concluding presentation on CBM Outlook, India and Way Forward, which is going to be presented by Mr. Sanjay Kumar, who is the Vice President and Head at the Essar Oil and Gas Exploration and Production Limited. And he'd be sharing his experiences as well as expertise on CBM. Presentation on CBM Outlook in India and the way forward thereof. So we would be having this presentation from Mr. Sanjay Kumar, who is the Vice President and Head at Essar Oil and Gas Exploration and Production Limited. Mr. Kumar would be sharing his knowledge and expertise on CBM exploration in India. So handing over the screen and the mic to you, Mr. Kumar.
Thank you, ma'am. Thank you very much. Good afternoon to all. This is a brief outline of my talk. So to start with, I'll talk a little bit on rising gas demand and need for cleaner fuel. Followed by a very brief on CBM activities in India and across the globe. We'll also discuss some of the key technical parameters one needs to evaluate for before going into a full-fledged CBM development to ensure commercial success. I'll also give a snapshot on Raniganj development, where Essar is actively producing coal bed methane. I'll also share some of the learnings we have had in our journey, and finally end with some recommendations, a few recommendations for how to improve in future. Okay, so I go to the next slide. So we all know greenhouse gas emission poses a great threat to our health and environment. And government across globe, including India, they have set up targets to reduce greenhouse gas emission. So top right figure shows emissions from different energy sources in India. We have set out our target to be carbon neutral by 2070. In the medium term, our target is to reduce emissions by 1 million ton by 2030. So this can only happen if we start adopting different strategies. And one thing could be increasing our gas share from current 6% to 15% by 2030 in our economy. And coal-based methane enhancement of production from coal-based methane could be handy in this. So as we are talking about increasing gas production and moving towards gas-based economy, one should realize that our domestic gas production only caters to around 50% of our needs. And going forward, unless we focus on unconventional biomethane, this gap is only going to increase. And this is where, taking advantage of our prolific coal blocks and producing more and more CBM gas would be really handy. This slide gives you a brief snapshot on CBM activities across the globe. As you would see, CBM activities are happening in more than 35 countries around the world. There is a huge resource base of around 9,500 TCF. And some countries have really pioneered in this, for example, Australia. But we in India, we have identified around 33 blocks with a resource base of around 62 TCF. But out of 33, active work is only happening in 6 blocks, and those are being operated by Essar, Reliance, ONGC, and GECL. Current production is around 3 million SCMD, total production by all operators. So there is a huge room to basically expand in CBM. We do have a good resource base, so this gives a very good opportunity for us to increase gas production for the country. So coming to enablers in India, if you see, conditions have never been so favorable as now in India, with rich coal reserves. And we rank almost 5th in coal reserves in the world, along with 3 decades of learning curve. So we are active in CBM for almost 3 decades now. So we started first CBM activities in early 1990s, along with a huge focus on infrastructure development. So a lot of pipeline network coming up, city gas distribution picking up. So these things are presenting opportunity for us to produce more and more gas. And it's also connecting a lot of areas which are potentially could be target for CBM gas production. So in addition to this, government policies have been also very supportive in last 3-4 years. I will not go into details, but we all know that. So we are at a sweet spot of ramping up CBM gas production in terms of enablers available for us. Yeah. So before I delve more into technical, just to take you through a very basic concept for CBM. The left-hand side of the slide shows details on CBM, and the right-hand side more conventional system. So as you would notice that in case of CBM, both the source and the reservoir rock is same coal. And it's a dual porosity system with bulk of the gas, with all the gas absorbed on coal surfaces in the matrix, and the cleat system or the fracture system, which we call natural fracture system here. Those are the conduits where we have water stored, generally water, and basically cleat system helps us in getting the permeability in CBM system. So the flow in CBM system, it's a 3-step process. So the gas has to dissolve from coal surfaces, it has to diffuse from rock surface to cleats, and then finally it has to flow to the wellbore. Unlike conventional system where you have a mobile hydrocarbon in free state, and any amount of some amount of pressure gradient will help the fluid to flow to the wellbore. The curve here, the one which I'm showing, pointing out with hand signal, as you would see, in case of CBM, dewatering is key. So as we call in CVM, water is the main product and gas is byproduct. So you have to keep producing more and more water to depressurize the system, which would allow the gas to become free. And finally, the gas will flow to the wellbore. So usually in a typical CBM well, you would see increase in gas production for a good number of years. It stabilizes at a particular level, and then you see a decline. So this is a typical production curve for a CBM well. On the right, you could see this plot where in conventional you would have hydrocarbon production and then it will decline, water cut would increase. So very briefly, this was very basic of CBM development. Coming to critical parameters, there are a number of parameters which one needs to evaluate before coming up with a development plan for a CBM field. So obviously some of the key parameters are highlighted here: depth, thickness, rank, permeability, critical desorption pressure. So these are very critical parameters, and we use tools like core hole drilling, from where we acquire core and do analysis, formation evaluation, well testing. These three are the key buckets which would give us the basic data for understanding a CBM field. In addition to that, geochemistry and geomechanics also becomes important, primarily to understand the origin of the gas, whether thermogenic or biogenic. Geomechanics is critical to understand stress direction, and more so in CBM field, all the wells have to be fracked. So these parameters needs to be understood. Sorry, excuse me. In terms of depth, CBM fields, you would see that most of the successful CBM ventures are between 300 and 800. So the upper limit would be 1,000 meters. So 300 meter, 100 meter to 8,000 meter, that presents a good zone for development of CBM field. Primarily because in this different depth range, you would have sufficient gas content, and at the same time, good enough permeability to flow that gas. Thickness, as you would expect in a conventional system, is critical here as well. Rank of coal, sub-bituminous to low volatile bituminous coal is, as I would show in the next slide, is the most favorable rank of coal to produce gas in a CBM system. Permeability, again, as we discussed earlier, permeability in a CBM system comes from the phase clits in coal. So one has to understand the permeability and in order to understand the productivity. One key thing here is generating adsorption curve. As I said, the process here is desorption, diffusion, and then Darcy flow to the wellbore. So generating adsorption isotherm in the lab and understanding the gas content and critical desorption pressure will allow us to basically understand the reservoir and understand the dewatering stage, understand the gas to further understand the gas ramp up from the field. Yeah. This slide again captures some of the key parameters which we discuss in CBM fields. So on the left hand side, the plot which I'm showing, so it shows the gas volume versus coal rank, and as you would notice here, sub-bituminous to bituminous. This is the range where you get the maximum gas content as well as good enough permeability. The next plot, cleat frequency versus coal rank. Again, this clearly shows the cleat frequency, which is number of cleats per meter, that nearly peaks in low volatile bituminous coals. So this is where low bituminous coals become important in terms of producing CBM gas. The next cartoon shows how CBM gas is absorbed on the coal surface. Once you depressurize the system, gas saturation builds up, and then it diffuses into the cleats. The next plot is showing how it diffuses into the cleats, and finally it will flow into the wellbore. On the left-hand side, the bottommost plot, the one which I'm showing here, this is typical adsorption curve showing the gas storage capacity versus pressure. As you would see the red dot here, that's the gas content which has been measured for that field. So you would see here from this field, in order to produce gas, one has to really depressurize the system from 1500 psi to 500 psi. So this amount of work has to be done before the point moves to the desorption curve, and you start seeing gas breakout in the reservoir. So CBM poses a great challenge, and you require a lot of dewatering. You would be lucky if some systems are saturated. Right from beginning, you can get a gas from that kind of reservoir. But most of the field, you would have to do a lot of work, a lot of dewatering before you start seeing gas production and incline in gas production. I talked about the cleat system and the phase cleat system. It is important to understand. I mean, this is the most critical thing in CBM, because all the permeability, all the productivity would be coming from this. So your well design has to be in such a way that you are able to intersect these cleats. Your frac design has to be such a way that you're able to intersect these cleats and improve productivity from CBM reservoir. So data gathering, I mean, this is a typical, amount of data, cross-functional data which you would need in order to go for a full-fledged CBM development. I have categorized into 4 categories: geological data, geophysical, rock mechanics, and well testing. In geological reservoir, although a number of parameters have to be known, but as a bare minimum, gas content corrected with proximate analysis, absorption isotherm, and cleat studies would be very useful for developing the field. Similarly, in geophysical, bare minimum would be gamma, sonic, and resistivity. But I would also add for CBM the 4-arm caliper, micro resistivity images, and dipole sonic, again critical to understand stress direction and cleat direction, because this is what will determine productivity of the wells. So this is also critical. Again, the rock mechanics studies is required for the frac design. Well testing, again, CBM, you have to we as a process, we drill core hole as part of exploration, and we do appraisal wells. We call that test wells here in CBM. These test wells, the objective is to understand productivity, permeability of the system. So, and these are very critical, because based on well test data, you would design your future development for the block. Coming to Raniganj block. This is geological map of the Raniganj block, and as you would notice here, 3 players are active in this block. To the east, this block, Durgapur, Essar, we are active here. We are producing coal bed methane from here. In the south, you have GECL, and in the north, you have Raniganj, you have ONGC active here. In terms of stratigraphy, this is a typical stratigraphy of Raniganj block. The 2 coal-bearing formations are Raniganj formation and Barakar formation. We at Essar are producing from Raniganj formation. We do have a shale section here. We call it Barren Reserve Shale. I think one of the operators has established gas presence here, and we are in planning stage right now. And we would be exploring this shale further. So the block is, so as you could see, 3 operators are active. So it's a very prolific CBM block. And although we have done, we are active here for last more than 15 years, there are a lot of things we are still learning, and there is a way, a lot of way forward. We have to catch up in terms of improving productivity from the field. In terms of a large part of the block still remains underexplored. So we have to do a lot of exploration wells and come up with development plan for the block. So just a brief, again, a brief on current status of our block, and a little bit of history and current status. So the block was awarded in 2002, and we went through a typical project life cycle of a CBM field. Currently, we are in production phase. We have 348 wells drilled in the field. Current production is close to 0.78 million. And we have compression facilities up to 3 million SCMD installed here. As we speak, we are making plans for infill wells in the block. And also, we have done some exploration in last year. And we have drilled core holes in step out areas. The plan is to drill more and more wells in this block and ramp up production up to 3 million in next 2 to 5 years in this block. So the below block diagram is showing typical gas. The gas from the wells are getting gathered at group gathering stations. We are removing moisture and then compressing it and selling it to customers, different customers at different pressures. So accordingly, the compression capacity has been installed in our group gathering stations. Next slide. Yeah. So some of the key technological interventions which we have carried out, which are worth mentioning here, is about refracturing and radial drilling. So we have carried out refracturing in many of our wells, primarily because based on our analysis, we could see that some of the initial fracs were really compromised, both in terms of design and in terms of how the well was flowed back after fracturing. But there is also a concept that after a production of around 10-12 years, near well stress regime, there is a change in near well bore stress regime, and refracturing would connect the well to some new more plates and enhance production from the well. We have, as we speak, we have done this activity in number of wells, and initial results are very encouraging here. Likewise, we have carried out radial drilling in 6 of our wells. Initial results have been mixed, but still the project is under evaluation as we speak. For future, we are looking for enhancing recovery from the field, and we are doing we have collaborated with Dhanabaad and carrying out lab studies as we speak for microbial flooding for enhancing recovery. And we are looking at some chemical solutions as well, which will allow us to basically improve productivity as well as accelerate desorption in the system, leading to higher production, accelerated production from the block. So these are the things we are working on as we speak. Some of the learnings I want to share here regarding well spacing. So typical well spacing globally, which at least I have encountered, is what I've seen is that 80 acre to 160 acre and even more. So based on my understanding, what I would recommend is that if we are confident on the borehole data, on the gas content data, on the saturation data, on the productivity, one should start at a lower spacing, typically around 30 acre, I would suggest, mainly because, see, in order to get a gas peak, you need to have more wells for sure. But in CBM, interference is good. So well interference helps in rapid desorption because in the reservoir, when you are depressurizing the system with multiple wells, you get faster depressurization and more desorption in the reservoir, which will ultimately help in accelerating gas production. So well interference is really good in CBM, and especially in greenfield development, one should acquire data judiciously and then start with a lower spacing. That would be a recommendation based on our learning. The other thing is on critical CBM data acquisition. Most companies do acquire gas content, saturation, and proximate analysis data, but I think focus has to be we should equally focus on rock mechanical properties as well as cleat orientation data. I mean, we have had a lot of failures because these data were not available, and now industry players recognize this. Definitely, it comes at a cost, and CBM being a marginal economics, we have to really improvise and come out with solutions for these. Similarly, again, commingled versus selective completion, and this has been a debate for conventional and unconventional both. But in addition to rock properties here in CBM, we have to also look at the saturation data. So when we combine seams together and produce from the wells, one has to really look at the saturation data. In one particular seam, it may require more work done, more depressurization before you come on the absorption curve. Or in the other seam, you may be more saturated and you may require less work done. So we should not be clubbing these two seams together. So some of these learnings are there, and accordingly, one should combine seams when one goes for commingled completion. Likewise, seismic, I mean, we don't have luxury of a lot of seismic data in CBM blocks, but a bare minimum of 2D seismic inline crossline for some structural control is required, because faults do play a very important role. We have seen some wells giving a lot of water. In order to understand that, we need to understand the structural settings, especially near the fault. Well, behaviors are different. So we need to have some amount of seismic data as well. Dewatering, as I said earlier, CBM water is primary product and gas is byproduct. And invariably in oil and gas, people.
So, two more minutes.
Yeah, I'll quickly wrap it up. So dewatering again is key. Well integrity in CBM. CBM fields are known for a lot of downtime, primarily because of nature of the coal, nature of the system we are dealing with. So we need to ensure that our well integrity is proper so that we are able to carry out well intervention activities. Otherwise, we will lose the well. Similarly, well stimulation, refractoring is one thing which we are doing, acidization and all those activities. We have to improve upon those. We have to look for right stimulation techniques here. In terms of production operation, I did talk about, key for improving production performance of CBM well is to run them continuously. It is very, very critical because in this kind of system, reabsorption, resaturation happens. So you have to run the wells continuously. Power reliability would be very important here. The other thing is that baseline water analysis, not only for the coal seams, but also the interbedded sandstones. It is very important because in some wells we have seen more water production. In order to differentiate whether it is coming from coal seam or sandstone, you have to understand that. And that is another area one has to focus. Production monitoring and analysis, one has to appreciate that CBM are being marginal economics. There is hardly any real-time monitoring with most of the operators. So one has to really come out with critical parameters which you need to monitor continuously. And also with improvement in technology and cost going down, one should look at implementing real-time technologies for CBM fields. Again, in interest of time, well design, again, deviated, vertical, horizontal, all have different challenges. But yeah, in our field, we have a lot of deviated wells and they have produced well. We have seen good productivity. We are planning for more horizontal wells. Deviated wells do pose challenge in terms of run life. We have improved upon completion to take care of that, but we need to do more. Similarly, completion PCPs were pretty much given for CBM development, but one can improvise, one can add hybrid anchors because again, these wells, CBM wells, are known to produce a lot of sand and gas. So to improve main life between failure, we have to improve upon the completion. Frac design, some of our learnings are listed here. 2040 mesh sand, and we were earlier using 1630. So we have improved upon that. Use of resin coated sands to prevent backflow during dewatering, backflow of sand. So that is critical. Well stimulation is one area where we need to still do more work. Refractoring has shown good result. High rate flushing has shown good result. But again, acidization, acid stimulation is one area we need to understand further. We have had very limited benefit with this, although we see scales in our field. So coming to conclusions and recommendations, again, CBM being CBM fields, they are very marginal in nature. So the focus should be to bring down the cost. And this can only happen if we set up some kind of platform for knowledge and resource sharing between operators, create technology hub and material hub so that the technology is readily available, materials are cheaper, and infrastructure development. Although we have made rapid progress in last decade, we need to do more work in this area. Similarly, collaboration with academia is critical, and especially for the enhanced recovery process. Although in conventional enhanced recovery process has moved a lot, CBM being upcoming thing, microbial flooding or CO2 flooding, chemical treatment. So we can look at those processes more. Similarly, in terms of policy reforms, as you would appreciate, that a lot of these coal blocks are densely populated, and you have a lot of forest coverage in these areas. So getting environmental clearance, forest clearance, and land bank for forest diversion in one go, this is very critical, and you would see a lot of these issues in existing CBM blocks. So one has to solve that. One thing which I would like to highlight is for the regulator is that primary data acquisition. In CBM bid rounds, I think there should be more focus on gathering of primary data by the government, by the regulator, so that the bidders can evaluate the block with more confidence. So in terms of gas content, saturation data, or more and more borehole data, some seismic. So basic work. If the government and the regulator can add that, maybe that will give more confidence for the bidders, and they can bid for the blocks more confidently. So thank you. That was my talk.
Thank you, Mr. Sanjay Kumar. Really a very exhaustive presentation on all the aspects of CBM exploration, as well as production, as well as regulatory aspects of it. And of course, data being the foundation on which we do our assessment of the current possibilities as well as the future strategies. So thanking you once again. And we have one question, of course, which was answered by Dr. Collett, because the question said, will oil shale kind of mining technique help in better production scenarios for the gas hydrates, which is aptly answered by Dr. Collett here. So as I do not see any other queries at present, so the organizing team would be forwarding any queries which would be coming up subsequently, and the emails are being shared. So once again, thank you for a wonderful presentation, sir. And handing over for the summing up of the session to the session chair, Shri Pinakadhar Mohapatra. Thank you.
Thanks, Sushma. Extremely well conducted this session. And it was really a fascinating session with so many renowned speakers and the best in the industry. It's really, really tough to sum up, and also we are running too much behind the schedule. So I'll only speak some 3 or 4 key things, starting from John, what he said, that the putting on the landing zone. He shared the experience from the North America. They took 20 years before they found out that the middle silt zone is the key. Prior to that, they were drilling many horizontal wells, not getting enough good result. But when they learned the lessons and put the wells in the middle silt zone, and then that became the turnaround. And in fact, the whole shale and the tight oil and tight gas put the North America from one of the major importers to net exporter now. And can India see that? To that extent, I think Utpalendu brought out some very, very key the imperatives. One of them, I think, we have to treat the unconventional separately from what we are doing in conventional oil and gas. So the phrase he coined, that plan, do, then review, learn and repeat. That's the key to how to handle the unconventional. And also I like his suggestion for a total review of the potential in India, because we can't rely on somebody from outside without proper the data. And then we keep on carrying those kind of figures forever. Instead of that, I think we have enough people and with enough data, and this is the time to go for a thorough review of the potential and then plan accordingly. And also his suggestion for review of the fiscal policy, I think that's a very, very critical suggestion, because the key thing in unconventional is the long-term investment and also the staying power, because it needs a lot of cost upfront, and then you have to stay in the game for long, like they stayed for 20 years before they found the landing zone in the North American. That kind of thing will require the motivation from government by changing the fiscal regime. Like, I think I must thank the government for changing that in CBM. Now they have given a waiver of the profit petroleum share to windfall gain. I think this is high time we have to do something like that in the sale or the tight oil and tight gas, because otherwise this is not going to take off. And coming back to gas hydrate, I think I must compliment Dr. Collett for a nice presentation, and also very happy to learn that KG Basin has the thickest gas hydrate in the world. And so that tells us the potential what we have. And then I think world over, in my opinion, we are in the threshold of cracking the technology for production. I think once that happens, then India will be in one of the best positions to take advantage of the gas scenario what is there in gas hydrate. Towards that end, I think NGHP3 we will have to plan and carry out shortly, because that is where we will have our plan is to go and test the gas hydrates what has been discovered in KG, Andaman and Maharadi Basin. I think coming back to CBM, in my opinion, we are at the tipping point of CBM, and Sanjay brought out that very, very nicely, because we have enough experience for last 20 years. We have done all the technical learnings, and there are some above ground issues as he brought out, whether it is the land acquisition and then the creation of a technology hub, the knowledge sharing amongst operators. They are all very, very good ideas. I think we will, whenever there is a monitoring committee to capture all the action plans, I think we will definitely take care of your suggestions. So once again, thank you, John Dolson, Dr. Collett, Utpalendu, and Sanjay for very nice presentations. And I am sure this session will be a watershed moment for the unconventionals in India. And finally, thanks, Sushma, for conducting the session so nicely, and also the whole organizing committee to have given us this chance to be part of this very, very important session. Thanks a lot, and all the best for the future endeavor.
Thank you so much, sir, and thank you to all the presenters.